Welcome to Calculations in Thermodynamics, using the examples from Giancoli's physics book, 7th edition. This is the first half of the chapter. The first thing we're going to look at is the first law of thermodynamics, which combines added heat, work being done by a system, the change in internal energy of the system, and all forms of energy in the first place. This left half of the equation is actually the equation for conservation of energy in a system. Setting the conservation of energy equal to heat added and work done allows you to calculate numerous variables. Example 15-2 deals with the kinetic energy transformed into thermal energy when observing a bullet entering a tree. A 3-gram bullet traveling at a speed of 400 meters per second enters a tree and exits the other side with a speed of 200 meters per second. Where did this bullet's lost kinetic energy go, and how much energy was transferred? Well, we can immediately identify a number of variables, Pe, Ke, Q, and W. So let's take a look at how we would do that. Well, first of all, the object is moving, so there's no potential energy involved, which means that Pe must be 0. Okay. There's no work being done on the system or by the system, and there's no work values given, so the work must be 0 as well. There's no heat being added to the system. This is not necessarily a thermodynamic state in question, so Q must be 0, which means we are left with kinetic energy and internal energy. Since Q and W and PE are all 0, we're only left with KE and U, and this is what it would look like. KE, change in KE, and a change in internal energy are equal to 0. So if we set them equal to each other, delta U must be equal to negative delta Ke. And since Ke's formula is quite simple, we can substitute in the mass and velocities for each portion of the Ke, which leaves us with a formula looking something like this. Now that we've got this all settled out, we can just apply our values and solve the formula. Your answer in this case is 180 joules. When dealing with isobaric work values, we can look at a series of different variables. Again, isobaric means constant pressure. Okay, now work is equal to force and distance, and force is equal to pressure and area. Therefore, work must be equal to pressure times area times distance. But area and distance is volume, which means that the work is also equal to pressure times the change in volume. This is going to be particularly useful in situations where you're dealing with a constant pressure change. Okay, not necessarily a change in pressure, but a change in volume due to a constant pressure. This example, 15-4, looks specifically at isobaric and isovolumetric processes. In this particular equation, we are compressing an ideal gas slowly at a pressure of 2 atmospheres, from 10 liters to 2 liters. Heat is then added to the gas, holding the volume constant, and the pressure and temperature are allowed to rise until the temperature reaches its original value. In this process, calculate the total work done by the gas and the total heat flow into the gas. Well, we have already stated that work equals pressure times a change in volume, and pressure is given in atmospheres. But atmospheres are a unit of their own. To be able to work with work or joules or volume, we must convert into pascals. The conversion factor for pascals is 1 times 10 to the 5th newtons per meter squared. So in this particular case, 1 times 10 to the 5th times 1 will give you, or 2 rather, because it's 2 atmospheres, will give you a value of 2.02 times 10 to the 5th. This is your pressure in pascals. Your change in volume, as stated in the original equation, is 10 liters to 2 liters. So your change is going to be negative volume. So we set these equal to each other. Now 1 liter is equal to 1,000 cubic centimeters, or 1,000th of a cubic meter. In this particular case, again, work equals pressure times a change in volume, which results in this equation. From here, we can just solve with simple arithmetic. And there's your answer. Negative 1.6 times 10 to the 3 joules, or 1.6 kilojoules. Okay. In example 15-5, we're looking at the work done in an engine. Now remember, engines typically are adiabatic. So in this engine, 0.25 moles of an ideal monatomic gas in the cylinder expands rapidly and adiabatically against the piston. In this process, the temperature of the gas drops from 1150 degrees Kelvin to 400 degrees Kelvin. How much work does the gas do? Now, the pressure changes, so we can't use any kind of equation that deals with a constant pressure. The change in internal energy is equal to the heat added minus the work being done. Now, we can reset the value of delta U equal to its derivation from temperature, which is 3/2 NR over times delta T. Delta T in this particular case was just re-illustrated as TF minus TI. If it's an adiabatic process, your Q equals 0 because there's no heat lost or added, which results in this equation. The work being done is negative, based on the value of 400 minus 1150 degrees Kelvin, and your resulting answer is 2300 joules negative. Now remember that a change in internal energy is equal to negative work being done, and if negative work being done is negative 2300, the positive work value must therefore be positive 2300 joules. The gas is doing work, pushing against the piston, pushing it away. In example 15-6, delta U for boiling water to steam. What we're looking at is a change in internal energy based on boiling water. The question states, determine the change in internal energy of 1 liter of water at 100 degrees Celsius when it is fully boiled from liquid to gas. This results in 1,671 liters of steam at 100 degrees Celsius. Assume the process is done at atmospheric pressure. Okay, well, first things first, this is a phase change, so we're dealing with energy. Secondly, 1 atmosphere is great for pressure, but we need to work with pascals. So, from the table of latent heats, you can find the latent heat of vaporization of water. Okay, we convert our atmospheres into pascals. And then we follow a series of steps. The first step is to calculate the heat added through the use of that latent heat and the mass of the liquid in the first place. Secondly, we'll calculate the work based on pressure and a change in volume. Third and finally, we will calculate the change in internal energy based on the first law of thermodynamics. So, let's take a look at this. Step 1, calculating your change in heat. Since 1 kilogram is equal to 1 liter, the mass of the fluid is 1 kilogram. The latent heat of water, vaporization, is 22.6 times 10 to the 5th joules per kilogram. Now we can just plug in the values. 1 kilogram times the latent heat of water gives us the value of 22.6 times 10 to the 5th joules of energy. Now again, your joules of energy are the only unit left because kg over 1 times 1 over kg, they nullify. In step 2, we're going to take our formula, our values here, and we are going to start applying things. Here we're looking for pressure, work rather. We know that the pressure is 1 Pascal. We know that the change in volume is based on its full liter and the amount of steam. So here's your value. Here's your value of steam minus the original value, the original volume. And now we can just plug in pressure times change in volume, resulting in a value of 1.69 times 10 to the 5th joules. And in step 3, what we're going to do is we're going to combine the answers from the first calculation and the second calculation into one final equation, and we're going to solve. Q is equal to 22.6 times 10 to the fifth joules. That was our step 1 calculation. Our step 2 calculation was calculating the amount of work being done, 1.69 times 10 to the fifth joules. Now we're already in the same unit, which makes life easier. The formula for change in internal energy is heat added minus work done. Now all we have to do is plug in and calculate. 22.6 minus 10 to the fifth minus 1.7 times 10 to the fifth results in a value of 20.9 times 10 to the fifth joules heat added to the equation, to the water. This has been the first portion of thermodynamic calculations based on Giancoli's Physics, 7th edition textbook, Chapter 15. I hope you enjoy and join us for Part 2.